My name is Malachi Dyer, and this is my 7.3 presentation on angular motion, on which I will cover planes and axis, center of mass, levers, and finally a gymnastics analysis. With this presentation, I hope to explain and analyze all of the topics with using descriptions, visuals, and examples to give a complete understanding of these topics within biomechanics. Firstly, I want to talk about angular motion within biomechanics. Angular motion is the motion of a body about a fixed point or fixed axis. This is seen a lot within sports, and in basic terms, it is movement around a curve. This can be seen in a 200-meter sprint, where the athlete's ankle will be performing angular motion along with their hips and knees. This is because it works around an axis. Other examples could be a bike during a cycling race. This occurs in a wheel of the bike, as it will be moving around an axis which allows it to move in a circular motion. Angular kinematics is the study of rotational motion in absence of forces. An example of when this can be utilized in sport could be within figure skating, when performing a triple axel jump, which requires 3.5 rotations. Aspects that could be studied in angular kinematics within this movement could be the conservation of angular momentum and angular overcoming inertia. Lastly, angular kinematics is the study of movement. Angular kinetics is the study of movement with other forces. This can be seen in a golf swing by analysing the athlete's muscular applied force, acceleration, and more to generate the angular motion of the golf swing. Planes are invisible flat surfaces that slice the body into different sections. There are three main planes of motion. First is the sagittal plane, which can be seen on the left. This splits the body into a left and right side. This applies to movements such as flexion and extension, where the body travels along this plane. The second is the frontal plane, which splits the body into an anterior and posterior side. This applies to movements such as abduction or adduction, where once again it will go along the plane. So this one on the right here. The last is the transverse plane, which splits the body into a superior and inferior sections. This can involve movements like rotation and also part of circumduction. All of these planes will generally match towards a specific axis. So now if we move on to axes, we find that axes are imaginary poles that go through the body at certain points to show the direction of movement. Firstly, we can match the sagittal plane with the mediolateral axis. So we look at the one on the right here. First, the frontal plane will match with the anterior-posterior axis. This one here. In the middle, this axis allows for movement alongside the frontal plane. So lastly, we have transverse, which matches with the longitudinal plane. Longitudinal axis, sorry, which travels from the superior to the inferior part of the body. This allows for movement alongside the transverse plane. Now we know the planes and axis, and which have the tendency to be together. I will show you some examples of when it is used in sports. My first example is of a baseball pitch. So specifically the throwing arm within baseball. The elbow joint will perform flexion, which is a movement within the sagittal plane. As we know, the plane splits the body into a left and right side. The sagittal plane has the tendency of being matched with the mediolateral axis, which is demonstrated through the elbow performing flexion around this axis. The mediolateral axis is a line that travels horizontally on the elbow joint when in the anatomical standing position. Another example could be of a figure skater performing a pirouette. The trunk will perform rotation, which is performed in the transverse plane. The transverse plane splits the body into a superior and inferior section. This is then linked to the longitudinal axis, which enters the body through the top of the head and then goes straight down, so it goes from superior to inferior. A final example could be of a swimmer about to dive into water as they perform a double abduction of their shoulders. This is performed in the frontal plane, which splits the body into a posterior and anterior side. This is then linked to the anterior-posterior axis, which goes into the anterior side and comes out the posterior side. Moving on, the next few slides are going to be about the development of angular kinematics. So first of all, angular distance is the total angle that has been travelled by a body or object around an axis. This measures through degrees. So an example of this could be through a bike wheel that is spun round half of its circumference. This is 180 degrees of angular distance, as a full turn would equate to 360 degrees of angular distance. Another example, this could be through an F1 car that has turned its wheel 100 degrees forward. This could equate to 100 degrees of angular distance. As distance is a scalar quantity, there is no sense of direction. However, when this is needed, there is angular displacement. Angular displacement is just the vector version of angular distance. This means that it has direction. It has a sense of the direction of where it's going, right? So we could talk about this swimmer. We could talk about this could be described through a swimmer. So a swimmer's ankle during freestyle. This is because it travels around an axis. It will travel around 90 degrees, which will equivalent to 90 degrees negative of angular displacement. This is because it's a vector quantity and uses direction. Another example could be through a runner's knee. This also has an axis which it will travel around with an angular motion. So within these movements, both angular velocity and angular acceleration come into play. Angular velocity is the rate at which an object rotates around its axis. As we know, velocity is a vector quantity, meaning it has a sense of direction. This is measured in radians per second, or how many rotations or movements around the axis are made per second. An example of this coming into play could be shown by going back to the example of the bike wheel. If the wheel goes around its axis 30 times in 10 seconds, we know that using the equation of revolutions divided by the time, that the radians per second would be 3. Alongside angular velocity, there is also angular acceleration. This is the rate of change of angular velocity using time. Using the example of a bike, if the wheel spun at an average angular velocity of 0 radians per second, in the initial phase and ended up at 3 radians per second, the angular acceleration can be found by finding the difference between them, which is 3, and then dividing that by the time, which is 10 seconds, making it 0.3 radians per second squared. So moving on. Center of mass is defined as the point at which the whole mass of the body, or all the masses of a system of a particle appear to be concentrated. In physics, we can say the center of mass is a point at the center of the distribution of mass, also known as the balance point, wherein the weighted relative position of the distributed mass has a sum of 0. The center of mass typically allows the head and the trunk, typically follows the head and trunk, as these are the heaviest parts of the body. However, a performer can manipulate their center of mass through movement of the body parts. An example of this could be through a batsman in cricket who is trying to play a front foot shot. They will push their head forward and plant their weight onto their front foot, making contact with the ball to manipulate their center of mass to be in front of them, but still play in the line. It still be in the line of their base of support. The line of gravity will still be in line with the base of support. Another example of this could be through a 100-meter sprinter in athletics on the blocks, as they will push their hips up and push their head forward so their center of mass will be in front of them, which enables them to gain momentum quicker. So finding the center of mass means to find the point where the sum of all the relative mass is equal to 0. To do this, you will have to find the shape of the object. So the symmetrical shapes, such as a tennis ball, their center of mass is going to be in the geometric middle of the shape. Whereas, on the other hand, if you have a non-symmetric body, such as this shuttlecock, it will not be in the middle of the shape. It will lean towards the side where the mass has been concentrated the most. So in this side, it is the foam of the tip of the shuttlecock that the center of mass will lean to. So that's the difference between symmetric and non-symmetric shapes. Now, as I've said before, there are many ways in which a performer can manipulate their center of mass within their sport. These include changing their body position, such as squatting. Another way could be through adjusting limb position, such as raising an arm or sticking out a leg. Another way could be through their equipment the sports people carry, such as a cricket bat. An example of an athlete manipulating their own center of mass could be through a figure skater performing a camel spin, where they have to lean their head over and stick their leg out so they distribute their weight in a way that the line of gravity goes through their base of support still and keeps them stable. Another example, this could be through a cyclist who will push their center of mass forwards by leaning over. However, this will not be too far forwards. The line of gravity still needs to be in line with the pedals. This is because when they're in line with the pedals, it is much easier to push down because their weight has been pushed there above the pedals. This will result in the cyclist's momentum automatically going forwards because it's slightly forwards. This example can also be linked to angular motion, as the line of gravity will be going through the pedals, which are going around an axis to produce movement, as the center of mass has been manipulated to be over this. It will be easier for cyclists to create an angular acceleration as they can push their weight down onto it. This will result in a greater angular velocity overall, and overall velocity of the athlete. So we now know that another example could be of an external object, such as a cricket bat. Now, this cricket bat here, in the first preparation phase of this movement, it is outside of the body, causing the center of mass to be pushed back. However, in the execution phase of the movement, the bat is much closer to the body of the athlete, which means that the center of mass will be probably closer to their body. This will make them more stable as well. So now we're moving on to levers. So levers, we could talk about the fulcrum first. There are 4 parts of this. So the first one is the fulcrum. The fulcrum is where the lever is placed to get purchase. Now the second part is the load. The load is the weight being lifted. Now the third part is the effort, which is the applicator of the force. And the fourth is the lever arm, the bar that the load sits on, as we can see in all of these classes of levers. So now we have 3 classes of levers. We have a first class lever, okay, which I will explain later. The first class lever will have the fulcrum in the middle. Now, a second class lever will have the load in the middle, but a third class lever will have the effort in the middle. So let's look into more detail in the first class lever. So that we know now that the fulcrum is in the middle of this. It's in the middle of the bar, the lever arm, which means that the load and the effort will be on either side. Now let's look at the movement within gymnastics known as the iron cross. Now the iron cross, the fulcrum will be the shoulder joint. The muscle or effort would be the latissimus dorsi on the back, and the load would be the body weight of the participant. This would be the lever, the arm, going onto the body. So this would be an example of a first class lever. A second class lever, so this time the load is in the middle and the fulcrum and the effort are on either side. We could use the example of a deadlift to explain this. So the load would be the body weight and the weights, such as the barbell, right? The effort would be the latissimus dorsi on the back, the quadriceps on the